Hey guys, welcome to our second lecture on optimization. We're going to go over the slide that we haven't finished for last time. And really our goal is just to do a refresher of what we did and work through the examples that were left out. If you remember, last time we looked at optimizations and data flow analysis that support them. And then we did everything intuitively, trying to understand, how will the program should be optimized and what kind of information or data flow analysis we need to do this optimization. And then towards the end, we started formalizing this more strictly using equations over sets, data flow equations. And what you're seeing on the slide is the data flow equations for available expressions. The reason why I have it back is because all of the equations that we're going to be using will be more or less of the same form. So let's just review what's involved, and then we're going to go through the examples that we haven't covered. So each equation defines the following sets. We have for each statement a set in, which is a set of data flow facts that flows into the statement. We have a set out, which is a set of data flow facts that flow out of the statement. So in is the information that we know before the statement is executing, and out is the information that we know after the statement is executing. Now, the exact content of in and out depends on what kind of data flow analysis we're doing. For example, if we're doing available expressions, which is what we needed to do for common sub-expression elimination, then the in and out sets contain expressions which are available in, expressions which are available before the statement, out, expressions that are available after. For a very simple statement, basically all that it does, it takes its in and copies it into its out. But for more complicated statements, a statement itself can create data flow facts, and it can invalidate other data flow facts. And to express that, we have a set gen that represents all of the data flow facts which are created by the statement. These are facts which may not necessarily exist before the statement, but are definitely true after the statement. And then we have a set kill, which represents all of the data flow facts which, if they were true before the statement, they are no longer true after because the statement has somehow affected them. And so the equations is basically a data flow fact that flow out of the statement is the set of the in data flow facts together with everything new that's generated minus everything that is killed. Okay? And this is what the equation for out basically says. There's one other thing, which is we need to figure out how to deal with multiple predecessors. In these examples, in these lectures, we're assuming it's a straight line code, but the equations are still defined for a more general case. On Friday, we'll do examples where we actually have multiple predecessors. Here, we're just imagining that we do. And so we need to combine the outs from multiple predecessors into one. And in the case of available expressions, we do it by intersection. Okay, so let's go through the next example. The next thing that we wanted to do after common sub-expression elimination is copy propagation. But first, let's look intuitively at the piece of code that we'll be analyzing. Then we'll talk about the equations for copy propagation, how to set them up, what they should mean, and then we'll work through the details of applying them. So our example is this code here in this piece of code. And what we are trying to do is we notice that at line 3, the statement is what we would call a copy. T is copied into U. After the statement, U is a copy of T, or U equals T from this point on. And then what we would like to do, we would like to find out how long this equality holds. Is it true in the next statement, a statement after it, and so on? And then whenever we find where it's true, we would like to propagate that copy over. And essentially, we want to replace this U by T, right? Because that would be a more optimized code. So this is what we're working with. So now let's look at the equations for copy propagation. First thing that we notice is that the equations are the same as for available expressions. Now, this is not a coincidence. The equations always have exactly the same form because the data flow facts, just even from the name, you can sort of see that it's a string of things that flow from into the statement and out of a statement. And the equations will just connect how in and out are connected. that the equation has the same form, but the meaning of what's a data flow fact, so what is an element of in and out, the meaning of what a gen and kill are, of course, will be different. Because if the equations are the same, and in and out and gen and kill are the same, then the result is also the same. But copy propagation is not the same as available expression. So here, our data flow facts are copies. For example, we had an example that we had u equals t. This will be our data flow fact. Now, there could be multiple u equals t statements in our program. And to separate them, to make sure that we know whether it's which particular copy it is, we're going to index everything by their line number or somehow some other way just to separate them. For example, here in our example, this will be u3. And it's u3 because it's a u in a third line right here. And the second thing is that we don't necessarily need the equality part. We don't need this part to be captured in our data flow fact. Because we know this is u3, if we look at the line, we see that t is already part of it. When we're going to write our data flow facts, we're only going to use the left-hand part of a copy. Our data flow fact will be all variables that are copies of other variables indexed by the line number. In particular, in this program, that progressively is getting messy with my annotations, but in this program, if we look at it, there's only one equality, u equals t. So there's going to be only one data flow fact, and it will be called u3. All of our ins and outs will be such data flow fact. What copies flow into a statement, what copies flow out of the statement. We're going to combine all the ins using an intersection because we care about a copy that is true no matter how we reached a given statement. So that's an intersection from all of the predecessors. Gen is easy. A statement that happens to be to create an equality. A statement like this, like the one at line 3, will be generating u3. Other statements don't generate anything. And kill is a more interesting one. So let's think for a little bit what kill should be. So kill is something that invalidates equalities. I think I have an example through. So let's just follow the slides to see what the kill is. So kill is going to kill any data flow fact that depends for which a statement reassigns any of its variables. So in particular, whenever we have a data flow fact u3, it will be killed by a statement that changes u, clearly, because then u is no longer the right assignment, but also by a statement that changes t, because at this point, again, u no longer equals to t. So here's an example of our kill set right now. So this particular guy, this guy, has a kill set of u3 because it changes the value of t. And since we have u equals t as a possible data flow fact, if we change t, then that data flow fact is killed. Now again, remember that when we set up those equations, when we think about the kill and gen sets, we think about them relative to all of the data flow facts that we have, independently of how they are ordered in the program. In this particular small snippet, you would look and you say, well, I don't care that u3 is killed by statement at line 1, because after I actually execute statement at line 3, I'm never going to execute statement at line 1 again, so it doesn't matter what it kills. But whenever we do the analysis, we don't think about it in these terms, because we think that the program may contain loops, and therefore a flow may go back from line 3 back to line 1, and maybe we just don't see it because we're looking at a small snippet of a program. Dealing with loops, this is what we'll talk about on Friday. It's part of a bigger iteration strategy that we're going to use. But the gen and kill and in and out sets are all defined locally, so that we don't have to worry about how the whole program evolves. We just define them locally relative to the data flow facts and what each statement is doing. And so it looks a little bit unintuitive. Why do we care that kill 1 kills u3? But we care about this because we pretend that we don't know how the full execution looks like. Now, there may be a question, why do we need to kill also when t is changed? Why do we need to kill a copy of u? And here's an example where we're taking the same program as before, but we added this extra line in here. Sorry about this. So we have an extra line in here. And in this example, it's clear that we can no longer copy propagate an assignment from line 3 to its use at line 5. That is, we cannot replace this by t, right? This is no longer okay. And that's, of course, because t has been reassigned. And so even so u3 equals t at line 3, u3 no longer equals t at line 5. So we would say that this line, the kill offset of 4, kill of 4, is u3. Right? So that's an example where the kill is actually needed, because without it, if we would say that kill is empty of 4, then the result would not be correct. Okay, so now once we have our gen and kill sets, all that's required from us is to solve the equations. And now at this point, everything becomes mechanical. And the mechanical part is on purpose because this is what we implement in a compiler. And we can only implement things which are mechanical. So here's our equations. We have an equations for in out, and we have a big equation that connects in and out and gen and kill. And so all we have to do is plug things in. So so let's see. This is what our equations look like. So let's assume that in from the beginning is empty. Right? The in of 1 is something that we have to decide. Either it comes from whoever the predecessor of this code, or it comes from the beginning of a program where maybe nothing is yet, no copies are yet set. So whenever we do this analysis on paper, for the first input, we have to decide that some assumption. Sometimes we're going to assume that it's empty. Sometimes we may assume that it's something else if we're part of another analysis. And then the rest of the equations are very straightforward. In of each next one is out of the previous one. And that's because we're dealing with straight line code. So there's no real intersection to talk about. We only have one predecessor. And then we have an equations for out. So now we have to solve it. Let's see. So there you go. We have our gen sets in here. We have our kill sets in here. And again, we said that there's only one equality. So there's only one gen, which is at 3. And there's only one time we reassign variable that is part of that equality, which is at line 1. And so we only have one non-empty kill. And now we have everything that we need to solve. At this point, there is no loops. So we can solve it by substitution, Gaussian elimination. All that we do is we look for the first thing that depends only on things that are already solved, plug everything in, go through the set operations to compute the output set, and we get one more thing solved. And we keep going on and on and on until we eventually solve everything. So let's do this example just a little bit. So here we know that in 1 is already solved. So we go to this equation, out 1. For in 1, we get an empty set. Kill doesn't matter because minus kill, empty set minus anything is going to be an empty set. Gen 1 is here, is an empty set. Right? And so out 1 becomes an empty set. And again, intuitively, this should make sense. We said that the only time we generate a new data flow fact is if we have a statement that is an equality between two variables. The first statement is not an equality between two variables. That means it can only pass data flow fact through. It can kill some and pass some others. But in our assumption, the input to it is nothing, is empty set. So it passes the empty set through, and that's it. The same is going to be for 2. Out 1 is now an empty set. And so this disappears, and this disappears, and now 2 becomes an empty set. Now, something more interesting happens. So we now need to compute out 3. So in 3 is an empty set. So let me cross it. Kill 3 is an empty set. Let me cross it. But gen 3 is U3. So I have to put it in here. And that means out of 3 is U3. And in of 4 is U3. And then we plug it in here. So in of 4 is now U3. Kill of 4 is empty. Gen of 4 is empty. And out of 4 is U3. Again, the intuition of it should be clear. The only thing to do is just follow the equations and see that the equations exactly capture the intuition, and try to get a feeling for it, how the equations actually do that they are quite intuitive. Basically, we assign U3 to T, and then we, in the next statement, we have that available. The next statement just uses U3, doesn't change U, doesn't change T. So U3 equals T remains true after that statement. So this is the same as our worked out solution. So we can come up and we said that at the out of U3 at this point, U3 equals T is available. And at this point, U3 equals T is available as well. Right? Except to simplify the notation, we write just U3 because we know equals T, we can get it from the program. So finally, we have this result. Now we want to do the optimization. And so we want to know what we can optimize. Okay, so let's see, there is a question that, okay, so there is a question, why other variables, T, A, and B, in this case, E, A, and B, don't appear in the genset. And here they don't appear in the genset because this is copy propagation. That's the name of our analysis. So we only care for copy propagations, what copies are propagating. And by copy, we mean exactly this, an assignment where we assign one variable to another. So the only gens are copies that are created by a statement. Statement 1 and 2 don't create any copies. Statement 4 doesn't create any copies. And only statement 3 creates a copy. Okay, so now let's apply the copy propagation optimization. So the idea here, again, we have all of these results that we computed, and we're looking whether there's anything that is redundant. For copy propagation, we look at an intersection of what's available and what is used by a statement, which is the intersection of in of a statement with the use of a statement. Here we'll see that for the last statement, what flows inside is a copy, U3, meaning that U3 can be represented by a different variable, not U3, but, well, in this case, T, but just some other variable. And we also see that it's used. So actually, the statement uses a copy instead of using a primary representative, which is T. And so that's how we know we can do an optimization. And for any place like this, we replace U by T. Right? So for any data flow fact that we have here we happen to have a U. So we know in the statement we replace U by T. If we'd have more data flow facts, then we would replace more variables as appropriate. Okay, so this is end of copy propagation. So I'm going to wait for a minute to see if there's any questions. And then we're going to move to reaching definitions, which is similar, but there is a subtle difference in there. All right, I don't see any questions, so I'm going to continue with the next thing. So the next thing that we need is reaching definitions. Reaching definitions is what we need for that store elimination. So we're going to try and find out which stores or assignments to variables we can eliminate because they're not used anywhere. And to know whether they're used or not, this is what the reaching definition analysis will do. So again, we have our equations. There is one big thing that's different, which is this guy in here. We're going to get to it in a second. Let's not start with it, but definitely that's a big difference. But let's look at the rest and let's look at what the similarities are and what the data flow facts should be. We have ins that are defined as some function of outs, union, not intersection. And we have outs, which is defined as everything that we generate together with everything that came in, except for everything that we kill. Okay, so the equations have a very similar structure. Now, what we propagating the data flow facts here are the definitions of variables. Now, what's a definition? So whenever we have an equality, like the one, say we had there, U3 equals T, we say that this equality is a definition. We call it a definition because sort of from us, whenever we have x equals y, we say that's a definition for x. And as you already saw here, whenever we talk about individual variables, we're always going to say that this variable has a particular line number. And those variables don't change. So U3 has only one value until we get to the statement again. And so this equalities or any statement or any equality statements like this, if I have, for example, A equals B plus C, in data flow analysis, those things are called definitions. So think of a definition just as an assignment. It's stable. It doesn't get to be reassigned. So for reaching definitions, what we want to know is which definitions, which assignments to variables get to various places in our program. So what we manipulate is these definitions. That means the data flow set, the data flow factor definitions. In is a set of all definitions that flow into the statement. Out is a set of all definitions that flow out. So in is what we get in. Out is whatever definitions we pass along and whatever definitions we create. Gen is a set of definitions computed by the statement. In our simple language, this is just going to be always gen is either empty because the statement doesn't define anything, or it's going to be exactly one new definition because the statement is just equality. It's assigned something somewhere. And kill is a set of all definitions which are killed by the statement, all definitions which no longer are available because we've changed something because we've reassigned. Now, there's a big difference here between available expressions and reaching definitions, which is in how things are aggregated, union versus intersection. And this has a lot of repercussions, but let's first think about the intuition. What is the difference? For available expressions, what we're trying to do is we're trying to find common sub-expression that we can eliminate. So if I'm a statement, let's actually look at this picture. So if I'm a statement right here, and I want to know what expressions are available to me, well, I don't know how a control gets to me. Either it goes through P1 this way, or it goes through P2 this way. If I want to say that certain expression is available, it should be available no matter which way I get to S. If something has to be available no matter which way we get to it, then that's an intersection. We only can use something if it's available on both sides. Now, for available, for reaching definitions, on the other hand, I want to know when a store that I made is no longer used. I want to know whenever I put something in some variable, that thing will never, ever, ever be used again. In this case, when I'm looking at a statement as whatever is, if something flows from at least one of the sides, then that definition is reachable at S. And if S can use it at some point. So that means that the combination that I want to do is a union rather than an intersection. I want to know that the definition may get somewhere, and it doesn't matter if it always gets to there. Okay, so with this in mind, let's try and do an example. So remember, we still have this piece of code in here. This is after common subexpression elimination. That's when we get T. And this is after copy propagation. So that's why we replace the use of U by T. And now we're trying to discover that U equals T at line 3 is a dead store and can be removed. So we need our gen sets and kill sets. Our gen sets here are variables being defined, which are basically these guys for each individual statement. And a kill set is any other definition of the same variable. So if we reassign a variable, if we reassign, for example, B, then we kill all previous definitions of B. If we reassign A, then we kill all previous definitions of A. So let's look at this. So here, just to make the example more interesting, we're going to assume that in of 0, or gen of 0, which gives us the in of 0, already has some definitions. So we assume that x, y, and z have initial versions of this definition somewhere here at line 0. Right? So this is to indicate that basically before we start our analysis, at this point, well, x, y, and z has to have some value. Otherwise, this code does not make sense. We then go and compute the gens for each individual statement. So gen 0 is given. That's why it looks so strange. Gen 1, 2, 3, and 4 comes from our definition. So gen 1 is T1 because that's a variable being defined. Gen 2 is A2. That's a variable being defined. Gen 3 is U3. And gen of 4 is B4. Kill set is empty because no variables are being reassigned. Remember, we only have a kill set if a variable that we're generating has already been assigned. But there's nothing like this happens in here. Okay. So, and here's an example of where we would need to have a reassignment. So here, for example, if we add an extra assignment in here, assignment to U at line 4, then of course it means that the definition, this definition, U3, does not get to here because it is being redefined at line 4. And so then we would say that at line 4, the kill set would include U3. But since no variable is reassigned, we don't have such a thing. All right. So now we get our equations. Again, the equations are very straightforward. The only thing to remember is that in this case, we have a union. If a definition can be used at some point, we just want to know that it can or may be used, not that it's always available. And then the equations for out, gen, in, and kill are exactly the same. Okay, so we start building our equations. So let's see. So in 1 is just given. It's x0, y0, z0. And then in 2 is out 1, in 3 is out 2, in 4 is out 3, right? This is because we don't have predecessors. So we don't actually see the disjunction, the union. We're going to see this on Friday. So let me erase my annotations here. And the out equations are exactly how they are. To solve, again, all that we do is Gaussian elimination. We simply plug things in and move them through the formulas. So we know what inf1 is. Because we know what inf1 is, we can plug it in here, subtract kill1, which is empty in our case, and then combine it with gen1, which is T1, right? And so the output here should be x0, y0, z0, because nothing got killed, together with T1. And now once we have out 1, we can plug it in here. And we're going to get in 2. We plug in 2 in here. And we get out 2. And so on and so on. I'm not going to draw this on the slide because this is just too messy. So we're just going to look at the solution that's already on the slide. So this is our gen sets. Kill sets are empty. And this is what we get in here. that basically as this code runs, more and more definitions are reached. Eventually, whenever we get to in4, x0, y0, z0, which were initially, together with t1, a2, and u3, are all reachable at here. Okay? Meaning that there is at least one execution on which the value of the corresponding variable comes from a definition at a corresponding line. So now we get to that store elimination. And so in order to do this, what we're doing is we're going to compute all the live stores. And the live stores are stores that create definitions that are actually potentially used somewhere down the line. And then the dead stores will be simply all of the stores which are not live. The complement of live stores is dead stores. Again, to do this, we compute an intersection of in and use of this analysis. And so we'll see that, for example, for the first statement, the intersection of in and use is x0 and y0. And what that means is that x0 and y0 are definitions which are available for line 1. So whenever line 1 runs once, sometimes, at least in one execution, the value of x comes from x at line 0. The value of y comes from y at line 0. And x and y actually used. That means we really need the value of x and y at line 0 because they are used in some execution, so we can't remove them. And then at line 1, we get t1 and z0. This is the two definitions which are used. At line 3, we get t1. And at line 4, we get t1 and z0. Now, live stores is the union of all of these guys. This is everything that is live. All of the things which are actually used. Dead stores is all of the definitions which are defined, which are part of our data flow facts, but are not live. So we take all of the ones that we have, subtract live, and this is what we get for things which are unused. Now here, there's two things. One thing is clear. Okay, so now U3 is a dead store. This is a dead store. It's a dead store in this program so far because its definition is constructed at some point. So that's why we have U3. But there's no place where it is actually used. There's no statement whose intersection of in and use is U3. So nobody is using it, but an assignment is happening, so that store is dead. The second thing that may be a little bit more confusing is that these stores, A and B, are also dead. And of course, if we look at this code, we analyze this code in isolation. We just assume that x0 and y0 are available on in, and that's it. And so obviously in this piece of code, A and B are in fact dead. They're not used anywhere. And that's because intuitively, when we're looking at this code, we often, when we look at a snippet, we think, well, more code is coming, and if something is computed, it will be used. But of course, here nothing is coming, and so that's why we don't have a use. If we wanted this to be more interesting, we could have added line 5 and created some use for A and B. For example, maybe if we print A and B here, then now we create a use for them, and now their stores will no longer be dead. So there is a question about Z0. Is Z0 a dead store? So the way we're doing dead store elimination, we're looking at variables which are looking at stores which are dead immediately. And once we remove the line that is dead, for example, if we get rid of this line, if we get rid of this line and this line, right? If we remove those guys, then at this point that becomes dead store as well. So we could have, and we talked about this before, we could have tried to define this analysis to be more optimal so that it iteratively removes all the dead stores. But it's easier to define it in this one pass where we compute the data flow equations, we look at the intersection, we decide what's dead, we remove those things. This is our optimization. And now we have a new program. And on this new program, we can repeat the data flow analysis again and potentially remove more dead stores. And this is what is usually done in compilers. So at least I know compilers such as GCC and Clang and how they work inside. And this is exactly what they do. The dead store pass usually cleans things which are obviously dead. And then the transformation happens, it changes the program. And then the data flow analysis is rerun. And depending on your optimization level, dead store elimination may appear once, twice, or may even sometimes be even run in a loop until eventually no dead stores are removed. Right? Similar to how you've done the simplification in Lab 4, for example. All right, and I think this is our last slide. So this is just a summary of what we had. So this is the full optimization pipeline. We start with the original code. The first thing that we do is we take the code, we build an abstract syntax tree out of it, and we basically reproduce this abstract syntax tree as a 3-address code. So the nice thing about the 3-address code is that every statement corresponds to a little subtree in an abstract syntax tree. So manipulating a program in a 3-address code is just like manipulating the AST of that program. We don't have to worry about expressions being very complicated or nested. We can just do it one piece at a time. And then we start our optimization pipeline. We compute available expressions. So to go from here to here, we compute available expressions. And from the available expressions, we can find out when we have an available expression that's incoming and is also used. And then we can apply common sub-expression elimination. Now, there's one fun thing about common sub-expression elimination is that here, the way optimization is done is kind of simple. We're just simply saying, oh, look, we have T that actually has a common sub-expression. But if you look at the analysis that we do, we don't remember that X plus Y is actually stored into T. And in fact, maybe if we change this code, and here we'll add some change to T, X plus Y is still available at line 3. But then optimization gets a little bit harder because then in order to optimize, in order to use X plus Y at line 3, we now need to also change T gets X plus Y to store X plus Y into some other intermediate variable because T is being reassigned. And we haven't talked about how the optimizations are done. We're really just talking about what is the data flow analysis that we need and what are the preconditions for an optimization. And then we're leaving the optimization itself, the program transformation, as something intuitive that you can do intuitively by hand on small examples, but we're not actually building a complete algorithm. So to avoid confusing you, I'm going to remove my change and then move on. After common sub-expression elimination, I think that that we might end up with is a lot of copies like this, a lot of equalities. U equals T, variable equals variable. And so then we do copy propagation. So here the analysis is also called copy propagation, and the optimization is called copy propagation. So the copy propagation analysis computes how far all of those equalities flow, at which point they may be used. And then the copy propagation says, oh, if I have a variable that actually is a copy of some other variable, I can change and use the original variable instead of a copy. So this is what happens here. And now after copy propagation, because we change how variables are used, it's possible that now we have assignments which are there because we introduce them by common sub-expression, but that's really not necessary because nobody's using them. And so here we will run available expressions. Reaching definitions. Keep mixing the two up. We run reaching definitions, our third analysis. And then we see which of the definitions are live. That is, which definitions at some point go inside some statement and actually used in a statement. And then we find out all of the ones which are not live. and this is a dead definition, so that this is a definition that don't reach anywhere, and so they're dead, and they become dead stores, and they're eliminated. So each optimization is informed by an analysis, and they're done in a sequence like this. And as was pointed out in one of the questions, each of our optimizations is not necessarily super optimal. That is, each optimizations may allow for another optimization to proceed, and the other optimization doesn't even have to be a different one. So for example, if we run one iteration of dead store, we removed some statements, and therefore we removed some uses, and therefore we possibly made other things dead. Instead of trying to create an optimization that is super optimal in that respect, rather we implement it in a simple way and iterate over it. So if we really want to eliminate all dead stores, we're simply going to iterate and remove dead stores, recompute reaching definitions, remove dead stores, and again. Now you may be worrying about whether this recomputation is expensive or not. It could be to some extent. But one thing that I'm not showing, which is a big part of real compilers, is that we're just concerned with writing down the equations for the data flow analysis and solving them. But in a real compiler, there's also an effort is done to maintain this information. So an optimization that, for example, removes statements may go and update what other data flow facts which are available. And so then you can run multiple times the same analysis incrementally, or the same optimization incrementally, each time updating the analysis results, as opposed to recomputing them from scratch. Okay, so there's a question whether a similar data flow analysis would be used for error checking, such as undefined reference for a function. And yes, absolutely. And this is actually also was described in the last lecture. For example, in a Java language, there is a requirement that every use of a variable must be preceded by its definition. And this is something that a compiler does as a static error checking. A lot of error checking is basically done at this level at the data flow analysis. The big difference here is that the data flow analysis for optimization, they focus very much on being efficient. So the big goal is to be polynomial time and run even within the polynomial time to run as fast as possible, because compilation times are really important. And if we move to error checking, there are some algorithms which are basically exactly the same. And this is what's used inside IDEs to give you red squiggly lines as soon as you type. But if we move into really bug hunting or vulnerability detection, then there the analysis get a little bit more advanced, because the requirement that they have to run very quickly is removed. And rather there's a requirement that they're good at finding those bugs. Okay, so this is the end of the lecture. So I'm going to pause a bit for questions and see if more questions come up. And otherwise, that's it. Okay, so there's a request. So somebody asked me to go to that store elimination slide. By the way, I create a live stream channel for each individual lecture, just so that people who are not doing it live, if they later want to go back and try and see what were the questions, if it's not clear from my answers, so that they don't have to get confused between different streams. Okay, so there's a question again, why is A2 and B4 are not live, they're dead, but are not removed? And so there's two parts to it. One is, if we were doing that store elimination on this piece of code, then both A, B, and U would be removed. But when we were looking at this intuitively, when we had this code before, we kind of said U is a dead store, but we didn't say that A and B were a dead store. Nobody asked me before when I was doing the intuitive examples, how come A and B stay? And the reason why nobody asked me is because we implicitly assumed that A and B is going to be used later on. U, we kind of said, oh, look, it looks like it's only used in line 4. Probably it's not used anywhere else. So that's that. But A and B, because this is just a code snippet, right? It starts from nowhere. It ends in the middle of nowhere. We kind of assumed that A and B are probably here because they're used. And so this is why they stay in here. This is why I have line 5 in here, saying that, well, we kind of assume that there is some use for A and B. Maybe you print somewhere later, and that's why they were not removed. And for you, we assume that there isn't. But if the code would be just this snippet, then U is dead and A and B would not be dead. And also in the data flow analysis, they would not be dead. So if the code would be just this snippet, then all A, U, and B would be dead, and all of them would be removed. And if we extend the code snippet with line 5, then line 5 has a use of A and B, and that would prevent them from being dead. Okay? So the question, what is the difference between all of those analysis? So let's go back to the equations. Say this picture. Okay, so there's going to be the following differences. So this guy is not cooperating with me. So there's going to be, so the data flow analysis all will be defined using this kind of an equations. And there will be the following differences between them. One, what is the type of the data flow facts? Are those copies? Are those available expressions? Does it look like variables? Does it look like expressions or other information that we may be computing? So the content of all the sets, that's one difference. The second thing that will be different is the gen and kill sets. Depending on what analysis we do, each statement will have a different notion of gen and a different notion of kill. So you could think of gen and kill, it's a meaning of the statement relative to the data flow facts. Different statements have different meaning, and relative to different data flow facts, they have different meaning. So gen and kill are definitely different for each data flow analysis. Second difference is the confluence operator, which is this guy. It's called the confluence operator. It could be intersection or it could be union. There's a slide in here to summarize this. We have one example of such a thing. Available expressions is intersection. Reaching definitions is union. Whenever we have an analysis that something has to be true along all paths, or something where we know that that fact has to be true when we get to that line, that's an intersection, that's a must analysis. And whenever we have an analysis that has to say some fact is true because it's true on some paths, and so it may be true by the time we get to line, like the reaching definition. Say we're using a variable A, and we may be using the version of variable A defined at line 5. But we may be using a version of variable A defined at line 6. So that's a may analysis, and that's going to be the intersection. And there's one other difference, which we don't have an example of here, but we'll see one on Monday, which is that the data flow can flow forward from predecessors to successors, or it can flow backwards from end of the program up, depending on what kind of analysis we're doing. So that's the differences. So the data flow facts themselves, they're different. Gen and kill sets, definitely different. Confluence, intersection, union, and direction, forward or backward. Okay, any other questions? By the way, nobody commented if they want to have a live meeting where you can actually ask questions live and I can answer not through this way, but live. And so I'm not planning to have it, but if all of a sudden you say that you want to try something like this, let me know now and I'll try and set up a WebEx meeting for that. So there's a question whether common sub-expression elimination and dead star elimination are the only times we use this type of analysis. Well, or in terms of our optimizations, yes, this is the only ones that we use. But of course, you can imagine lots of other applications where you may want to know what expressions are available or what stores are dead. So they don't have to be used just for this. But yes, in our examples, this is the optimizations and this is the analysis that enable them. Okay, I don't see any more questions coming. If you have questions afterward, please ask them on CampusWire so that everybody can see the question. If there is, if you do want an office hour or if you want to have a one-on-one meeting with me, ask. That's possible. And I think that's it. I'll see you again. Well, I won't see you, but we'll meet again on Friday.